This is the fourth video in the stoichiometry section. This one's on limiting reagents. And to date, when dealing with stoichiometry, we've always made sure that we've had values of the reagents such that no reagent is left over at the end of the reaction. This is not real life. We don't always have the exact amounts of everything we need. The reagent that is used up first is called the limiting reagent, and that's because it limits how much product can be made. When the limiting reagent is gone, the reaction stops. The reagent which is not used up is called the excess reagent, and it's left over. And before we start with using chemicals, we're going to start by using colored dots. We're going to have red dots and green dots, and we're going to say that 3 reds plus 2 greens gives us this compound. And we frequently write it this way with the 3 reds on one side and 2 greens on the same side, and then the 3 reds and 2 greens together. But this sort of implies that nothing gets used up. In reality, you start with the 3 reds and the 2 greens, and they join together to make the compound, so there are no reds or greens by themselves floating around anymore. They are used up. We actually use up the reagents. So when we play stoichiometry and say, well, you've got 12 reds and 8 greens, you're going to get 4 of the compound. What's really happening is that you're starting with your reactants, and we're going to pretend that it takes place in a stepwise fashion. These reactants form this product, and so they're no longer there. And then these reactants form this product, and they go by. The same thing happens for these reactants, and they go bye-bye. And finally, the last set of reactants joins together, and they disappear. But we can account for all of the dots. Now, what happens if I start with 12 reds but only 6 greens? Well, we allow them to react, and the first set reacts, and you get this. And the second set reacts, and you get this. The third set reacts, and you get this. And then the reaction stops. We still have the 3 reds, but there are no more greens. Reaction cannot proceed. The limiting reagent is that reagent which is used up, thus stopping the reaction. And so here we would say green is the limiting reagent. The excess reagent is the reagent left over when the reaction is stopped. So here we'd say the red is left over. There's some excess remaining. Now a quick note, reagent is synonymous with reactant. So you may see the term limiting reactant, or I may say that, or I may say excess reactant, or you may read that. They are synonymous. If you're given amounts for more than one reactant, you must determine if a limiting reagent is present, and then all further stoichiometry is based upon limiting reagent. But now this does raise a question. How are you going to figure out what the limiting reagent is? And here's where I get to say stoichiometry. There are 5 steps to determine what the limiting reagent is. The first step, you need the correct balanced equation. So you need to make sure you have the chemicals written correctly. Convert all the grams to moles. Use the first reagent as if, and use the second reagent as the then. Pretend you don't know how much is for the second reagent. We're going to call that answer Z. Now you're going to compare your calculated Z to the actual number of moles of the second reagent. Z is the number of moles you need. There are 3 possibilities. Z is less than the actual number. The amount that you need is less than the amount that you have, so the second reagent is the excess reagent. Z could be greater than the actual number. You need more than you have, so the second reagent is limiting. Or Z is equal to the actual number. That means there's no limiting reagent. Both reagents will be used up at the same time. And the 5th step is all stoichiometry for any other calculations for that problem will be based on the moles of the limiting reagent. The best thing to do is jump in and do examples. So here we go. Suppose you're given 10 grams of hydrogen and 10 grams of oxygen, and you're told you're going to make some water. Is there a limiting reagent? I'll start with step 1. Write out the correct balanced equation. Once again, for my bookkeeping, I like to put the grams above the chemicals. Step 2, I want to convert all grams to moles, remembering that moles equals grams divided by molecular weight. So I do it for the hydrogen, put its value underneath. Do it for the oxygen, put its value underneath. Now I can go on to step 3. I'm going to use the hydrogen as the if. I'm going to pretend I don't know the oxygen. So I set up my ratios, I do my cross multiplication, the hydrogens will cancel, so yes, I'll be getting an answer for the oxygen. So now I'm going to take that 2.48 moles of oxygen, the Z, and compare it to what I really have. And it's pretty obvious that 2.48 is greater than 0.313. What I need is greater than what I have, so oxygen is the limiting reagent. So let's go to a second example where we're not only going to have to figure out the limiting reagent, but then use that to do further calculations. Here's the problem. You're given two chemicals, sodium carbonate and hydrochloric acid, and you're given amounts for both of them. This automatically makes you think limiting reagent. I've also given you the products. And the question is how many grams of carbon dioxide should be produced under these conditions? So start with step 1 and get the correct balanced equation, and there it is. I do my bookkeeping and I put the X above the carbon dioxide so that I remember that that's what I want my final answer to be. Now I'm going to convert all my grams to moles using the moles equals grams divided by molecular weight. I do it for the sodium carbonate. Then I do it for the hydrochloric acid, and now I'm all set to go to step 3, where I'm going to use the first reagent as the if and pretend I don't know the second reagent. I set up my ratios, and when I do my cross multiplication and division, I find that Z is equal to 1.3448 moles of hydrochloric acid. I now compare that value to what I really have. So I compare the 1.3448 to 1.500. It's obvious that Z is less than 1.500, so that means the hydrochloric acid is the excess reagent. Therefore, the sodium carbonate is the limiting reagent. And note, the sodium carbonate weighs more than the hydrochloric acid, but the limiting reagent is not based on mass. So now we're going to go to step 5, because the real question is how many grams of carbon dioxide do I need if I have this much sodium carbonate. That is a stoichiometry problem, and since it's based on the limiting reagent, I'm going to circle that once again to remind myself that that's the limiting reagent. So if I have 0.6724 moles of sodium carbonate, then how many moles of carbon dioxide will I have? Set up my ratio. It's a 1-to-1 ratio. So after cross multiplying and dividing, I realize I'm going to have 0.6724 moles of carbon dioxide. Then, of course, moles times molecular weight equals grams. Plug the appropriate values into the equation. Solve for the grams. I get 29.59 grams of carbon dioxide. I put that into its usual spot, so now I have numbers everywhere I need them, and I can say that 29.59 grams of carbon dioxide should be produced. I have one more example. I'm going to give you the problem, ask you to solve for the answer, give you the answer, then walk you through the steps. Here is the information. I want to know how many grams of cobalt-3 chloride should be produced. Stop, figure it out, then proceed, check your answer, and then I'll walk you through it. Go. And the correct answer is 165.8 grams of carbon-3 chloride should be produced. How did we get the answer? We followed the 5 steps. We started with the correct balanced reaction. I do my bookkeeping with the X to remind me of what I want for my answer. I'm going to convert all the grams to moles. So I do it for the cobalt. I get 2.443 moles. I do it for the sodium chloride. I get 3.008 moles. So now I'm going to see how much sodium chloride I really need. So I set up the ratios, cross multiply and divide, and I get Z equals 7.329 moles of sodium chloride. I'm going to compare that to the actual moles, and I see that 7.329, the amount that I need, is greater than the amount that I have, and so the sodium chloride is the limiting reagent. And so notice, even if you have more moles of a substance, it can still be the limiting reagent. You have to go through all the steps. So there's my limiting reagent circled. So now I'm going to base all my stoichiometry off the sodium chloride and the 3.008 moles. So if I have 3.008 moles of sodium chloride, then how many moles of cobalt-3 chloride do I have? Set up my ratio, cross multiply and divide. I get this value for Y. So I plug it in. Moles times molecular weight equals grams. Plug the appropriate values into the equation, and I get 165.8 grams of cobalt-3 chloride, and that was the answer we had at the beginning. So you just have to follow multiple steps. This is very, very stepful. So to review this section, if you're given values for more than one reactant, you must think and really calculate to determine if there's a limiting reagent. Remember that the limiting reagent is that which runs out first and that stops the reaction. The leftover is the excess reagent. If you know the excess reagent, the other reagent must be the limiting reagent. And there are 5 steps to determining the limiting reagent. And these are: make sure you have the correct balanced reaction. Convert all of your grams to moles. Use that first reagent as if. Use the second reagent as then, and we'll call that answer Z. Compare Z, what you need, to the actual number of moles of the second reagent, what you have. If Z is less than the actual number, the second reagent is the excess reagent. If Z is greater than the actual number, the second reagent is the limiting reagent. And if Z equals the actual number, you have the Goldilocks syndrome. You have just the right number of moles. And finally, any further stoichiometry is based on the moles of the limiting reagent. So that takes care of this video. There's one more video left in the section, and that will be on what is called percent yield.